Standard computing memory architectures often buckle under the weight of massive data parallelization. The standard retrieval model is strictly geographic. A central processor provides a specific memory address, and the system retrieves the single piece of data residing at that physical location. Modern routers and cloud databases require the exact opposite operation. The processor supplies a specific data word and must instantly find its stored physical address. Forcing a standard array to execute this search sequentially creates extreme latency and an immediate system bottleneck. Solving for high-bandwidth parallel access or instant data search requires physically altering the topology of the foundational memory transistor cell itself. Achieving modern compute speeds requires abandoning standard, dense memory structures. Engineers sacrifice physical silicon space to embed specialized logic directly into the storage layer. The common baseline for all high-speed on-chip memory is the standard 6-transistor, or 6T, SRAM cell. This schematic isolates the functional core of the 6T cell. These cross-coupled inverters maintain the binary state, continuously reinforcing the stored 1 or 0. To read or write that internal state, external bit lines, labeled BL and BL bar, are introduced. During a standard read operation, a voltage applied to the horizontal word line turns on the two bottom access transistors. Opening these transistors exposes a critical structural vulnerability. The internal state node is suddenly connected directly to the massive capacitance of the external bit line. The act of reading the cell physically risks flipping its stored data. This phenomenon is known as read disturb. Because of read disturb, a 6T cell cannot safely support multiple simultaneous read operations. As a result, the system's maximum data access bandwidth is strictly capped by the physical instability of the read mechanism. To increase access bandwidth without corrupting data, engineers developed the 8-transistor SRAM cell. Comparing the 8T schematic to the 6T baseline reveals the direct engineering solution, the physical separation of the read-write mechanisms. The two extra transistors on the right physically decouple the read bit line from the internal cross-coupled state nodes. The state node drives the gate, but never electrically touches the wire. This decoupled architecture provides the foundation for dual-ported SRAM designs. This diagram outlines a dual-ported cell, utilizing two independent word lines and bit lines. This topology allows the system to execute two independent single-ended reads simultaneously, or utilize time multiplexing to read and write on alternating clock phases. The physical trade-off is geographic. Adding more access transistors significantly increases the required silicon area per bit. Multi-ported arrays deprioritize overall density. They dedicate premium silicon real estate purely to moving data out faster while maintaining absolute read stability. Increasing the cell footprint with 8T or multi-port designs creates a compounding electrical problem when those cells are stacked into an array of millions. A massive, continuous bit line sharing thousands of access transistors carries heavy parasitic capacitance. This wire capacitance severely degrades read speeds and drives up dynamic power consumption across the system. The architectural solution to this is the hierarchical bit line.
The array is broken into short, localized bit lines. These short segments feed their data into a heavily driven global bit line, bypassing the capacitance issue of a single long wire. If cell-level topology compromises physical area for raw access bandwidth, array-level hierarchy is required to salvage speed and power efficiency from that expanded footprint. Multi-port topologies solve the problem of moving data out of the array, but the challenge of network routing requires finding data entirely in place. This requires content addressable memory, or CAM. It operates in exact reverse to standard SRAM. The architectural formula that makes CAM possible is explicit. The hardware requires both storage and an embedded comparison circuit. The controller broadcasts a single search word to all memory cells simultaneously. The array evaluates the input and instantly outputs the exact address location of the match. By embedding comparison logic directly inside the storage array, CAM effectively operates as a massive parallel computational engine. The physical manifestation of this formula is the 10-transistor CAM cell. This schematic breaks down the cell into two distinct zones, the upper SRAM storage layer and the lower XOR match logic layer. In the initial state of a search operation, the word lines are held low, and the horizontal match line is precharged to a high state. When the search key placed on the bit lines does not match the stored state, the XOR pull-down network activates. The match line discharges to a 0, registering a miss. If the input perfectly aligns with the stored state, the pull-down network remains closed. The match line maintains its high state, registering a valid hit. This 10T structure allows millions of cells to independently execute XOR comparisons in a single clock cycle. The array processes the query without moving any heavy data across the system bus. To handle advanced routing, the 10T cell is evolved into ternary CAM, or TCAM. TCAM adds a third encoding state to the memory logic, the don't care, or X, mask bit. This third state adds extreme flexibility to search operations. A search key of 10XX0 will instantly trigger a valid match across 4 separate addresses: 10000, 10010, 10100, and 10110. This diagram demonstrates how TCAM dictates modern network switch architecture. A search key enters the TCAM array, rapidly identifies the matching rule, and maps to an associated action or hardware port. High-speed cloud databases, real-time packet routing, and hardware-level virus detection all rely entirely on the parallel search capabilities baked directly into TCAM silicon. Today, hardware designers overcome the physical limits of 6T SRAM by bifurcating its evolution into 2 distinct branches. The access path isolates state nodes with 8T and multi-port topologies to guarantee stable concurrent read bandwidth. The search path embeds XOR logic directly into the 10T cell to execute massive parallel queries. Both paths demand a steep price in total silicon area and transistor count, strictly limiting memory array density. Memory arrays now serve as the frontline computational engines of the digital world. By reconfiguring the topographical arrangement of transistors, engineers have integrated logic into the storage silicon itself.